we can say that very simply. That within a system, the sum of the heat changes is equal to 0. Or if I only have two substances involved, Q hot plus Q cold equals 0. Now we're going to use a piece of equipment called a calorimeter. Now we've already used a colorimeter. Calorimeter differs by one letter, okay? Instead of an O, it has an A for the second letter. This is a calorimeter, a calorie meter, if you want to think of it that way. So we're going to measure heat changes. And a calorimeter basically is a system that doesn't allow heat to go out of our system or heat to come into our system. Now, it can be a very fancy setup, or it can be as simple as a styrofoam cup. Okay, styrofoam cup actually works fairly well as a calorimeter. Okay, now we're going to have to look at two things, but we're going to start knowing our equation here. So let's take a piece of metal and put it in water and see what happens. All right. So what temperature should we put the metal at? What's that? Ooh, we're putting a cold piece of metal in water. Okay. So let's say we have a 0 degrees Celsius piece of metal. She said 273 Kelvin. Okay. And the water's at room temperature. Let's say we have this chunk of metal that is one of those listed in the table of the book, so I don't have to look it up someplace. Oh, come on. So on page 185 of the text, there are some heat capacities. And we'll see that aluminum has a heat capacity of 0.897. Iron is 0.449. Copper is 0.385. Let's use a piece of copper, okay? And let's say, oh, how big should that piece of copper be? What's that? 500 grams. That sounds good. 500 grams piece of copper, and let's put it in a liter of water. At room temperature, which is at 22 degrees Celsius. So if I do this, I'm going to have heat go from the water to the metal, right? And doing this, I can calculate what the final temperature would be of this system, assuming no heat goes out of the system or comes into the system, right? Okay. So how am I going to do that? Well, I know that Q for the metal plus Q of the water is going to be equal to 0. Okay. Now, is it possible that there will be some heat change based on the styrofoam cup it's in? Yes, and we could actually add a third term in here where we determine the heat capacity of the calorimeter. And some calculations will be expected to do that, but we're going to simplify it at the moment and look just at this. Now, if I take these two and add them together, I get 0, right? Okay. Now, this is going to be a fun problem because I'm asking what the final temperature is going to be. And I have an equation that has delta T. What is delta T? Well, delta is the change in, right? Change in temperature, which means final temperature minus initial temperature. Now, if the copper and the water are in the same thing, we're going to assume that they get to the same final temperature, right? So how many final temperatures do we have? One. How many initial temperatures do I have? Two. Okay, so I'm gonna have to take that into account. So Q for the metal, I have 500 grams. Now remember our equation, MC delta T. M, 500 grams. I guess we only have three significant figures. Times C. Now again, I have to look in the book here, but C for copper is 0.385 joules per gram degrees Celsius, or joules per gram Kelvin. I probably should address that. If I go from 1 degrees to 2 degrees Celsius, what's delta T? That's 1. If I convert both of those temperatures to Kelvin, that would be 294 Kelvin to 295 Kelvin. What's delta T? 1. So a delta T in Kelvin and a delta T in Celsius will have the same value. Okay? So if I calculate my delta T in Celsius, it will be the same as delta T in Kelvin, right? Okay. So what's delta T then? Do I know my final temperature? No, that's what I'm looking for. Do I know my initial temperature? What's the initial temperature of the metal? And I'm going to add to that the Q for the water. I have a liter of water. Anybody know the density of water off the top of their head? Well, remember the first lab that we did where you measured the density of water and you all got something that's like 0.999 something or whatever. We're going to assume to three significant figures, the density of water is 1.00 grams per milliliter, right? And if I have 1 liter, that's 1,000 milliliters. So at 1,000 milliliters and 1 gram per milliliter, I have 1,000 grams. Now, I'm not going to write it here. I really should write this as 1.00 times 10 to the third grams of water, but I'm just going to remember three significant figures. So 1,000 grams of water times specific heat of water times delta T. Well, delta T is final minus initial. What's my initial temperature? 22 degrees Celsius, and that's equal to 0. How many unknowns do I have in here? 1. So it's time to do some algebra. I'm going to let you guys work on the algebra a little bit. I will work on it at the same time. Okay. Pull out my handy dandy calculatorial device. So this one worked out a little simpler. Usually we don't get lucky and have a 0 here. That's why I left it in Celsius. So if I have a 0 here, when I multiply by 0, what do I get? 0. So I only have 2 TF terms and one term that doesn't have a variable in it. Usually I'll have 2 terms here and I'll have to combine them, separate them to different sides of the equation and solve for it. So when I do this, I find that the temperature of water has gone down significantly to 21 degrees Celsius. Wow, copper doesn't hold a lot of heat, does it? Okay. Copper actually conducts heat quite well, but it doesn't take much energy to heat up copper. Okay. We are going to actually do calorimetry. I think I got an email or 2 about what lab we're going to do this week. We're doing the calorimetry lab. We're going to measure heat changes. Isn't that fun? Yes, we will have exactly 1 whole day of lecture before we start in on the lab, but that's okay. We'll be able to do that. So what we're going to be doing is calorimetry, but we're going to do a little bit more than that because I've still got time left. I can cover more stuff. Yes. I took 4,184 times 22.
And you don't have to convert the Celsius to Kelvin.
Because it's a delta T. Okay. Normally I would go ahead and do this in Kelvin, but since I had a 0 here, I'm like, hey, I'm taking advantage of that. Anytime you can simplify an equation, go ahead and simplify it. But yes, you can do this in, because they're delta T's, you can use Celsius or Kelvin interchangeably. Okay. All right. So let's go a little further and let's look at how this all relates. Now, I've only introduced colorimetry, and I need to point out what would happen if instead of 0 degrees Celsius, somebody said, let's put 200 degrees Celsius. Would that be a simple equation? Would that just change one thing in this equation? If I put a piece of copper in that was 200 degrees in water, what sound would it make? It'd go shh, right? Why? Because some of the water is evaporating. We have to understand that in addition to heat, if we want to take an object and make it warmer or cooler, there's another place that heat has changes. And that's for a change of state. And I don't mean like if we go to the east and end up in misery, not that kind of change of state. Okay? So if we go from a solid to a liquid, I have to add energy to melt the solid. If I go from a liquid to a solid, it releases energy. If I go from a liquid to a gas, I have to add energy to go from a liquid to a gas. And if I go from a gas to a liquid, I give off energy. Now, those energies are, relatively speaking, the heat of fusion, or the enthalpy of fusion. Fusion is the change between solid and liquid, or the enthalpy of vaporization. Okay, and we will talk about those a little bit more. But because we're doing the lab, I do want to take into account that we are not going to be changing states in the lab. So I'm going to leave change of state for another day. And I want to talk a little bit more. Now, your book goes through the first law of thermodynamics and talks a lot about internal energy and heat and work. And I would think that that's really important that we know that all of that exists. We'll spend more time on it in another class. But for right now, we need to know that we have this thing called enthalpy. And enthalpy is a change of energy that takes into account the stored energy in chemical bonds and the heat changes associated with that. Actually, the heat and work changes associated with that. And this is known as enthalpy. Now, I can take let's say I take 8 CH4 plus O2. What state should we put water in? Gas, okay. Okay, if I do this, I am going to have a heat change. Now, you know that this is like the burning of methane, right? It gets hot. That means I'm going to have an enthalpy change. And I can list the enthalpy change for this. Now, if it's going to give off energy, generally speaking, we take a look at our reaction and we consider that the system. Is the enthalpy change for this going to be positive or negative? Well, this is going to give off energy, so it is going to be a negative value. And it just so happens that this value happens to be about 802.2 kilojoules per mole. We will learn how to measure that. Okay? Or how to determine that. But what's important is that I understand if it gives off heat, it's negative. If it absorbs heat, it's positive, right? And if we can figure out how to measure that, I can determine the enthalpy change for a reaction. As a matter of fact, I can also write it into my equation. And put it as a product, 802.3 kilojoules per mole. If I just write the enthalpy change with the reaction, that's one thing. If I write the energy change in my equation, we call that a thermochemical equation. Okay. Now, there are some reactions that you have to add energy to in order to get them to react. In those cases, it's called an endothermic reaction. This one is exothermic. An endothermic reaction would have the heat on the other side, and it would appear as a positive enthalpy change. We can also graph things, right? Because you guys like graphs. Yes? This one that's here is exothermic. The heat's on the right. If I have one that would have a positive term, it would be on the left. And I'm going to clarify that a little bit here with a diagram. Now, your book goes through and lists some diagrams, and it just uses up and down. I am going to take a look at the chronological process in a reaction. Okay, so this is going to be reaction progress. And we're going to make an abbreviation, okay? Because you know when you have a reaction, the stuff before the arrow are the reactants, the stuff after the arrow are the products, right? And if you abbreviate reactants, R-E-A-C-T, could you really abbreviate reaction anyway? No. But we're going to abbreviate it RXN. So RXN is our abbreviation for reaction, and if you see REACT, that's our reactants. Okay, that's just the simplified way we're doing it. And over here I have energy. Now I'm going to start with a certain amount of energy. So if I have, let's say I was going to burn this marker. There is a certain amount of energy that this marker would contain, right? Okay. And we're going to put that here. Okay. Actually, let me use a better marker. I'm writing in blue because my black markers are dying here. Now, there is something that's going to happen. We're going to look at that in a later chapter. All we care about is the beginning and the end. Okay? Now, what has happened here between the beginning and the end? Did I have energy go up or energy go down? It went down, right? So that means our system has had energy go out of it. What sign would that have? Negative. So this is an example. That's exothermic, okay? I guess I have one other color here. Now, I could also have a reaction like this. And what do I know about all this stuff that happens in here? We care about it later. We don't care about it right now. Okay, all we care about is the initial and final, because it's a state function. Okay, for the red one, what's the sign for the delta H on that one? It's a positive. So let me throw a fun thing out there. Which one of these do you think photosynthesis is? Endothermic, right? Okay. So we can store energy, we can take energy and we can put it into chemical bonds, or we can do reactions where we get energy from chemical bonds. Okay, both are important. And with energy flow, that's going to be fairly important for us to look at. All right. So I have introduced most of the topics in chapter 5. The remainder things that we need to do is, well, we need to be a little bit more specific with our calorimetry. Yes. Friday. Yeah. Oh, does Canvas not say Friday? Okay. Maybe I forgot to publish that. Chapter 10 assignment is due this Friday. Chapter 5 assignment will be due next Friday. We need to look a little bit more at calorimetry. We're going to actually do it. Don't you love how you get to like learn some of this stuff by doing it in the lab? Okay. So we're going to do some calorimetry this week. And let's go a little further than that. So in addition to the calorimetry that we're going to do, we're also going to learn how to calculate enthalpy changes for reactions. And there's 2 different ways that we're going to do that. Actually 3, because we're going to measure an energy change of a particular reaction. And we're going to look at some ways of doing that. But in reality, that's what we're going to focus on in chapter 6. Or not chapter 6, chapter 5. So chapter 5 is going to be dealing with just enthalpy changes of chemical reactions. There is an area called thermodynamics that has a lot of different terms. We're working with one of several. Okay, so thermochemistry, it's important enough with enthalpy that we spend an entire chapter on one term.